Okay, so just continuing on the SVMs, I only got maybe about 10 or 20 more minutes of SVM stuff, and then I'm going to talk about the cool stuff, which is a little more, it's basically just all theory. There's no really math there. But okay, so I talked about the kernel function, right? So the kernel function, the purpose of that is to transform data so that it's originally non-linearly separable to linearly separable. So what you have to do is you have to take, an input example which currently has n+1 features, and you transform them so that it becomes an m+1 feature vector, or m is the total number of examples. So you transform each example, which is x of I, into a new vector f of I, such that it looks like this. Right? So it looks like, so there are m+1 of these features for the ith example. Okay, and this is just the bias. Well, we just set this to 1 customarily, which is nice. So you get 1, and then each of these elements basically measure the the similarity or the kernel function between the current example with each of the other examples. So this is what are known as kernel methods, where you take an example I and then you measure the similarity with all of the other examples in your training set. Okay, so right here. So what this is here, so each element, except the bias, measures the similarity between example I with another example j from 1 to all the way up to m. Okay, so this is what is known as a kernel function. So you're creating a new vector where each element in this vector will measure the similarity between the example you're looking at, which is the ith example, with all of the other examples in your training set. So there's going to be m similarity measures between, for each of the examples that you have. So once you finally transform, or once you finally create this vector, all you have to do now is use this, and with the parameters that you trained, once you apply the kernel function to all these examples, you use this as the input into your SVM. So now, if you take this, you take the dot product of this with f. If this is greater than 1, then it's a positive class, right? Predict positive class. And if this is less than -1, then it's predict negative class. I haven't talked about multi-class yet. I'll get to that in the middle a little bit, but it's basically still one versus all stuff like we've talked about before. So once we have this, the new cost function is now. So since we transform this data into a new domain, we have to use a cost function to recognize this transformation. So the new cost function is now this. Okay, so this is now. So what you want to do is you want to sum over all the different costs between each of these new features. So we have max, so this is yes, okay, and then so this is the new cost function now. Okay, so what we're doing is we are summing over, so what we're doing here is that we're finding the prediction, so theta transpose f, so we're figuring out whether or not it's negative or positive. And the reason why this is 1 minus is because we're going to figure out what the cost associated is. So you reverse it, so if there's a prediction error, you add this on top of your cost. That's why there's a 1 minus here. And this here, this is what is known as the hinge loss. I'm not going to derive this, but I'll go into this in much detail. But this will be the new cost function you have to minimize. So this is what's known as the hinge loss. And you do 1 minus because if there are any errors or any mispredictions, you want to add those on top of the cost, on top of the error. So you have this, and then you're also subject to your constraints also such that, right, you have still this stuff that we talked about before. Okay, so you have these constraints here too. And we're not going to minimize this. It's actually much harder to do, to minimize this cost function, using the techniques using available techniques. So we're not going to cover that here. So let me just move this aside. If you actually take a look at either, Andrew Ring's course, the CS229, or Yasob Mustafa's course, they actually do cover the mathematics and actually how to solve this. So if you're curious and if you want to take a look at the detailed mathematics behind this, then go ahead and take a look at those courses. But I'm not going to cover that here. Okay? All right. So we have this, and then, so this is, you're just averaging over as many examples as we have. And then we also have this familiar term here. This is the regularization term. So it works in a similar manner with SVMs, but the results are actually quite different depending on what the term, what the term is. So regularization. So how it works here, it's going to be slightly different. So it's a trade-off between increasing the margin size and ensuring that each training example, this is actually, I've only got a couple more points here, and then I'm going to actually go through some code. That'll be relevant for Lab 3. Okay, so ensuring that each example is on the correct side, is on the correct side of the margin or the hyperplanes or whatever. Okay? So if you have a very small lambda, a small regularization parameter, what this means is that you are basically considering that the data is linearly separable. You're assuming that the data is linearly separable, and then you're just applying the normal SVM problem. Okay, so if you have a small lambda, it behaves almost like the linearly separable case. Okay. Oh, someone moved the, whoopsie. If you have a large lambda, what you're doing is that you'll prevent overfitting. It prevents overfitting, but may not be as accurate when you're doing predictions. When predictions are made on new examples. Okay, so I haven't talked about what kinds of kernel functions there are, and I'm going to cover that right now. So some common kernel functions are the following. Okay, whoops. Okay, so we have the first one is what is known as a polynomial. Okay, so it usually looks like this. So if you have two training examples, all you're doing is you're just taking the dot product between them, or you're just, taking the transpose of one and multiplying with the other. Okay, so this is the dot product. There's usually some constant associated to it, and then you raise this to the power of d. Okay, so this is some constant. And this is the degree. So there's a polynomial kernel. So that's one possible one. Okay. The next one is a Gaussian kernel. This is pretty much what you pretty much know what this is. Okay. So the kernel between two of these, it's just like what you expect. So the length between these two squared divided by, okay, so it's slightly different. So there's no mean associated here. What you're doing is you're just finding the length between the two vectors and just applying an exponential operation, squaring it and so on. So that's the Gaussian. And last but not least, there is the hyperbolic tangent. honestly, there's no one of them that will actually, there's not one of them that is, the most accepted one. You just have to try different ones and see what the accuracy is. So this one is, what is it? It's 10H. Then we have alpha xi. So the dot product between these two plus some constant, okay? And this is usually greater than 0, and this is usually less than 0. Just, usually. Okay, so those are some some common kernel functions. If you want to, there's lots of different ones, but you can't just randomly choose, just any random one and try to go for it, because there is a property that they have to satisfy. It's what's known as Mercer's property, where you have to use this property to be sure that you can actually use this as an acceptable kernel function to be used for support vector machines. But that's beyond the scope of this. But these all satisfy Mercer's theorem. So the polynomial, the Gaussian, and the hyperbolic tanh. But you can't just randomly choose a kernel and go from there, because it has to satisfy an actual theorem before you actually do it. Anyway. Okay, so you have this, all right? So now, if you want to predict a new example, okay, what you have to do is you have to transform the example using the kernel function and then predict. I didn't talk about this. I actually skipped over this by accident. So what I mean by this is that you'll create a new feature vector, right, such that, 1, so for a new example, x, right, so what you do is you're going to create a new feature vector where it finds the similarity between this feature vector with all the other examples that we have. Okay. We get a new feature vector, okay? And then all you have to do is if predict positive, right? And then finally negative. Okay, so that's how you do it. Well, that's just implied. Okay, last but not least, there's multi-class. It's actually pretty much the same thing as what we've dealt with logistic regression. So when you're dealing with multi-class classification, instead of training a bunch of logistic regression classifiers, you're going to train a bunch of SVM classifiers instead. So let's say you've got 4 or 5 different classes. What you're going to do is you're going to take an SVM and train it so that positives belong to that class of interest and negative belongs to all the other classes. So you have one SVM for that, and then you train a bunch of other SVMs. So you have n SVMs in total. And then if you want to figure out which class a new input is in, all you have to do is just take each of these take one example and put it through all of these SVMs and just choose whichever one has the best score or the best or the highest score, and that you would choose to be belonging to that particular class. So multi-class classification. Okay. So many SVM packages have multi-class built in. Okay, but if not, this is what you do. Adopt one versus all approach. Okay, and the procedure is very similar to what we've seen with logistic regression. Okay, so what you're going to do is you're going to train k SVMs, okay, where k is the number of classes. Okay, and then what you do next is create the vector, we'll create the labels, where, actually no, create the expected output vectors, not labels. Outputs to be, not vectors, but to be y equals 1 if class I is positive, not class I, but class if the class desired is positive. Okay, and y is equal to -1 otherwise. So you're going to train a bunch, okay? Then what you're going to do is you're going to get different parameters for each SVM, okay? And then all you have to do now is to predict the class of a new example. Submit each example to, no, submit this example, not each, to each SVM and choose the class with the highest score. So it's pretty much the same as logistic regression. So instead of having a bunch of logistic regression, classifiers, you just do it for the SVMs instead. Okay, so that's pretty standard. Nothing to write home about. Okay, all right. So I'm going to do some code right now, actually. So let me just bust open up here. Okay. All right. So what I'm going to do is, this is just a quick demo in order to show you how SVMs work in MATLAB. So this code I'll actually post online. It's actually part of the lab if you actually want to follow along. But what we're going to do here is just a very simple demo. So I'm going to do both the binary case and the multi-classification case. So the first step that we're going to do is just we're going to load in the data. So there's a predefined data set that's part of MATLAB, which is, as you've seen in lab number 2, it's the Fisher-Iris data set. But instead of actually loading it in from lab 2, it's actually built into MATLAB, so we can do that. So we're going to close all the figures. We're going to clear all the variables just to make sure that we're starting with a clean slate. And then it's called Fisher-Iris, the Fisher-Iris data set. So if you type in load Fisher-Iris, it'll load in the data set for you. And then when you load it in, there is a 150 by 4 matrix, which is stored in the variable MEAS for measure. And then there's also labels as well, stored in the stored in another vector. But anyway, so we're going to create the training example data. Okay, so this is a 150 by 4 matrix where we have 150 examples, and we have 4 features. So there's the sepal width, sepal length, and all that. So basically how it works is that the first 50 rows belong to class 1, the next 50 rows belong to class 2, and the last 50 rows belong to class 3. Okay, so let's see here. The labels are stored in a string array called species. Okay, but we're not going to take a look at that. But basically, so get the first 100 examples. So these correspond to the first 2 classes. Okay, so the first 50 elements belong to class 1, and the next 50 elements belong to class 2. Okay, and then we're only going to concentrate on the 3rd and 4th features because we want to just make this 2D for now, so we can visualize this. So what you're going to do is you're just going to basically do this. Okay, so we get the first 100 rows. So that corresponds to the the first 2 classes, and we get the 3rd and 4th features. And then what we're going to do is we're going to make the first class positive and the second class negative. So what we're going to do is we're going to create a label vector. So it's going to be, let's see here, 1s and then 0s. Okay? All right, let's see. Yeah, and okay. So the first class is going to be all 1s, so I just created a 50 by 1 vector of all 1s, and then the next one is going to be all 0s. Okay? So I'm going to plot these so you can see what they look like, and you can see that they're linearly separable, so plot these points to see how separable they are. Okay, so plot. So what I'm going to do is I'll plot the first 50 rows, so I need the first, let's see here. So it'll be, so I made a matrix, so the first column is the first feature. The next column is the second feature. Okay, and I'm going to give these blue dots, right? And then I want to plot the second set of features, or second set of examples. So first column, second column, I guess make these red, right? And then what I'll do is I'll make the marker size a little big. So I'll make the actual point size is 16. So when you run this, where are we? Okay. So that's what the points look like. So the first class I made blue, so this would be the positive class, and this is the negative class. So you can clearly see that they're linearly separable. So the SVM should be able to do this no problem. Okay? And this code I'll post online, of course. It's actually part of the lab too. So I'm going to so plotting those is fine. So all you have to do now, so let's see here. So 1, 2, create the matrix, and just let's see here. So I'll just put another directive here, plot the points. And then what we're going to do now is we're going to train a classifier. So train a SVM classifier. And the default classifier, okay, is linear. So this is assuming that it's linearly separable. So default is linear. So it's very simple. All you have to do is you have to call the function fit C SVM. Okay, so sorry. There we go. Okay, so fit C SVM is the function you use to train SVMs. It's part of the statistics and machine learning toolbox, but you should be able to have access to this. So all you have to do is you just specify you can specify, well, obviously you have to specify the inputs. So the first input into this function would be your training example. So each row is an example, each column is a feature, which I did. And then you specify for the second input the labels for each example. So first input is the data matrix, okay? And then second input is the label per example, okay? And then what I like to do specifically is I like to provide an optional input called class names. And what class names does is that you are physically telling MATLAB what the negative classes are and what the positive classes are. So what you're doing is you're going to look into your y vector and say, okay, so inside my y vector, the 0 is the negative class and the 1 is the positive class. So I like to specifically tell MATLAB to do this. So specify class names to tell MATLAB what is negative and what is positive. Okay, so it's a 2-element vector where the first element is the label that is negative and the second is positive. Okay, so I specifically said that the negatives were 0 and the positives were 1. Okay, the reason why this is nice is because it doesn't have to be numeric. Like for example, if you had, let's say, a binary vector, you can make false be the negative class and true be the positive class. Or if you have labels that are strings, like you can make one string being the negative and then the other string being the positive, so it's nice. It's very versatile. Okay, so when you do that, all right, so that actually, so its default is linear. So when you run this, oopsie, yeah, thank you. Train a, wow, fail, okay. Okay, so this SVM object has a bunch of different properties. So let's see here. So you have the different class names. You have the bias, which we talked about before, and then there's a bunch of different constructs here that I won't go into. But it tells you that the solver, it's sequential minimal optimization, and you can also figure out this array here tells you which elements were chosen as support vectors, which weren't, and then you have you've got kernel parameters and a bunch of all that stuff. So. But yeah, so it basically has an SVM object for you. So, you train an SVM classifier, and then what we want to do is let's plot these support vectors on top of the plot, okay? So if you want to access the support, so basically these support vectors are the points that are chosen in your data set that were chosen to fit the hyperplanes. So what you can do is SVM is the object that is returned to you, and there is a structure called support vectors, okay? And what that does is that it returns a matrix where each row is an example and each column would be a feature. So if you want, we can plot these on the plane, which is fine. So what you do is you do plot and then let's say marker size 16, I guess. Okay, so what this is, this support vectors here, so what this is a n×2 matrix where each row is an example that was chosen to be a support vector. Okay, so if you do that and you plot these, I'm going to put block circles over the support vector. So when you do that, you get this. So these two elements were chosen as the support vectors, which makes sense, right? So the optimal hyperplane would be, somewhere through there. Okay, so you created a SVM classifier. That's nice. So the next thing that you want to do is you want to use this to make predictions. So if I, let's take a look at these points. So if I were to choose, let's say, 1.7 and 2, or 1.7, 1.7 and maybe, 1.7 and let's say 0.6, for example, I would expect that the input would be probably positive. And if I chose, let's say, 4.5 and like 1.2, then I would expect the results to be negative. So what you can do is you can use a function which is called predict. That'll actually predict which labels you want based on the SVM that you've trained. So declare new examples for predicting. And see what the SVM model gives us for the labels. Okay, so I'm going to create a new vector, let's say 1.7 and 0.6, right? And then, and then maybe 4 and 1.5 or something, right? I want to make sure that each of them is linearly separable. So then all you have to do is use the predict function, where the first element is the SVM that you trained, and the second element are the points that you want to predict, okay? So when you do this, okay, that's cool. So this tells us that the first example is the positive, and the next example is the negative, which is what we expect. All right? So that's the binary case, which is nice. And then I'm going to do the multi-class case now. So it's actually pretty similar. So what we're going to do is you're just going to copy this. Okay, go to the multi-class. So that step's okay. But what we're going to do is we're going to, because there are 3 types of classes, what we're going to do is we're going to grab every single one. So there are 3 classes. So let's just grab all of the classes. But we're going to still use third and fourth features though. Okay, so we're going to just change this to that. So we're going to get every single example. Okay, so let's actually plot these. So let me see what these look like. So I'm going to take this here, right? Just going to copy this. And then, so this, and then I'm just going to do, right, so 1, and then the last 50. We'll make that green, I guess. Okay? All right. So here we go. So you have 1 class, the second class, and the third class. So between the first and second classes, there is a boundary of separation, but the second and third might be a little ambiguous, but that's okay. All right? Okay, so what we're going to do is we're going to train a bunch of support vector machines. So we're going to do 1 versus all. So you're going to have 3 support vector machines where the positive class belongs to the class that you want, and the negative class is everything else. So what we're going to do is we're going to store these in a cell array. So train SVMs. Okay, so the reason why I'm using a cell array is because you can think of them as dynamic containers. So they can contain whatever you want. And so usually with matrices, they store a bunch of numbers. With cell arrays, you can store any object in them. So the first element could be a matrix. The second element could be, like another structure. Or the third element could be another cell array. So they're dynamic containers. So you use cell arrays because they can contain anything. Okay, so what you're going to do is you're going to train the first SVM. Okay, so remember, so what we need to do here is we need to create a label vector. So instead of using 0s and 1s, I'm going to use true and false to show you how versatile this is. So what this does is that it creates an array of false. And then what you want to do is you want to make the first 50 elements equal to true because these belong to class 1. Okay, and then all you have to do is just use fit CSVM, and then you do x, y1, and then you specify the class names. But then you make this false and true because you want to manually tell MATLAB that false is the negative, and and then true is the positive. So training the first SVM is there, and then I need to train the second SVM. Okay, so you're going to do the same thing, but then elements 51 to 100 are positive. So you set this. Okay, these will run the class 2. Do the same thing. Yeah, I know. Yeah, sorry. Thank you. Just making sure you're paying attention. All right, just an extra typo. And then finally, we have the third SVM. So this belongs to 101 to 150, and then you just do 3. Oh yeah, and I got to change these as well. Okay, so you got 3 different SVMs. Okay, so now what I want to do is I want to predict, I want to be able to predict new inputs. So let's see here. So yeah. So this is 2 and 3. Okay. Cool. All right. So use one versus all to predict new inputs. Okay, so what I'm going to do is I'm going to create a data matrix. So I have 1.7 and what? I have 1.7 and I'm going to just take these, and then I'm just going to declare a third example. So I have these, and then if I take a look at the figure, maybe I'll make it like 6.5 and 2.5, just to be sure. So I want to declare 1 point in each class just to be sure that this is working. All right? Okay. Okay, so what you're going to do is we're going to cycle through each of the examples, okay? So then the predict function has a 2-output version where the second output tells you the score of how each example ranked with respect to the class. Okay, so what this means is that the first column tells you how likely it belongs to the negative class. Okay, and the second column tells you how it belongs to the positive class. Okay, so if you had, let's say, 4 examples, and what you can do is you can take a look at the second output, where the first column tells you how likely each of those examples belongs to the negative class, and the second column tells you how likely each example belongs to the positive class. So what you can do is you can do this instead. So we have SVMs, and if you want to access an element of the cell, use curly braces. Okay, so this tilde means that you don't really care what the labels look like. You want to take a look at the score because this is one versus all. Okay, and then what I want to do is create a score matrix where each column tells you how likely each example belongs to that class. Okay, so it'll be, there's 3 examples, so and there's 3 classes. So then what you do is okay? All right, so place the positive class scores in the right position in the matrix. Okay, because the first column is the negative, the second column is the positive, so I want to get the second column of the output of the predict function and put it in the right column for the scores. Okay? All right. Okay, so if I run this, okay, if you take a look at what scores looks like, this is what it looks like, all right? So what this is saying here is that each example is on the rows, and then each of the columns is the classes. So what you're going to do is you're going to take a look at each column and figure out which one has the largest response. So in this case, what we're seeing here is that the first example, the highest response is this one. So the first example should belong to class number 1. The second example here, it's saying that this is the largest number, so the second example should belong to class number 2. And the third example, this is saying that this has the highest output, so the third example belongs to class 3. So what you can finally do is find the labels. So if you use the second output of max and look along the rows, you get exactly the positions for each row, which was the maximum. So if you do that, so 1, 2, and 3. Okay, so what this does is that it looks at each row, figures out where the maximum location is, and it tells you what that position is. So this is saying that for each example, we have class 1 was the best predicted value, class 2, and then class 3. Okay, so this stuff is actually in the lab, so there's actually more details in the lab. I just wanted to show you how exactly you'd use support vector machines to run stuff. And this is just assuming the linear kernel. So in lab number 3, you can actually specify options to specify the kernel function you want. You can specify Gaussian, polynomial, that stuff will be all done in lab 3 for you to experiment with. But I just wanted to show you how to use SVMs here. So there's the fitc SVM function, which will train an SVM for you, and then there's the predict function, which will predict the labels for you, and there's also the score matrices and all that. Okay, that was a quick demo here. So that code will be posted. All right. Okay, let's get on to the actual good stuff. All right. Okay, so machine learning system design. Okay, so this stuff is, the important stuff that we want to cover. So suppose you, implemented, let's say for now we implemented linear regression with regularization. So let's say we implemented linear regression with regularization. Okay, so remember the cost function was, it looked like this, right? So it was, it was the hypothesis with the expected output, and then you also had the regularization term as well, right? So that's what it was in the past. Okay, so this was the cost function. Okay, so let's say you have a system where you use linear regression with regularization, but then when you try to predict new outputs, the error is really, really bad. So like the error is very high, or the predictions don't really match with what you actually seen in your training examples. Okay, so however, when you make predictions, on new instances, okay, in a test set, there are very large errors. Okay, so let's say you have a system that's trying, you found the right, parameters, but when you try to run this on the test set, it's making really bad results. So the question is, what do you do next? Well, there's several things you can try. First, you might want to decrease the number of features. It might be overfitting, or you might want to maybe decrease or increase the regularization term. Or you might want to maybe get more training examples, because you may not have enough training examples for this to be able to predict new inputs. Or there's a whole bunch of different things you can do. So, the one thing you could do is, get more training data. That might help. Okay, it depends on the situation. I'll talk about this later, but it depends on the situation. Okay, so again, more training data. You may not have enough data. To properly predict new examples. Okay, there's one thing. Yeah, put it there. You can also try varying the number of features. Maybe you don't have enough features. Maybe you want to add more in. That might be another example. You might, either add or remove. Okay, maybe try adding polynomial features. Maybe the decision boundary is nonlinear, so you might want to add some polynomial features to help you try to figure things out. Maybe taking the square of them and taking the product and so on. Maybe something like that. You can also try varying the regularization term. That's a possibility. Okay, but there are so many things to try that you could get more training data. You can try varying the number of features. You can try changing the regularization term, trying polynomial features. There's so many things you can try. Where do you actually start? What's the first thing that you should probably try to do? So there are so many things to try. There's so many things to try. There's so many things to try that, there's so many, which should we choose? Okay, so that's the question we'll answer later. So we also have covered many algorithms so far. Which algorithm do we choose? So those are the two questions that we're going to ask. one, if the performance is bad, what do we do to try to resolve it? And two, there's so many different algorithms that we've taken a look at, which one do we choose? So both of those questions we're going to address today. So to do that, to facilitate this, to make things easier, we're going to introduce something which is called the cross-validation set. Cross-validation set in your training example, so cross-validation data set. Okay. The cross-validation set. So far, what we've only done was we assumed that we had training data and test data. That's what we've seen so far. So training data are a bunch of examples you use to train your model, get the right parameters. And testing data would be used to assess whether or not your trained model can accurately predict new examples that it's never seen before. So we usually just split it up into training and test data. That's what we've seen so far. And it's worked for the most part. So far, we have only used training and test data. Okay? So, the training is used to train your model, get the right parameters. Training data is used to create a good prediction model. Okay? And the test data checks to see if we can accurately predict new examples. Okay? But then this training, so this assumes, everything that we've done so far, the labs and all that, it assumes that we know which algorithm to choose. So the training data and then test data, this assumption is only based on the fact that we know which algorithm we're going to choose. But we've covered so many different algorithms in this course, which one is the best algorithm to choose. So if you have, so there's neural network, support vector machines, logistic regression, linear regression, which one of all these four is the right one to choose? And that's where the cross-validation set comes in, because this cross-validation set will actually help you choose which of the algorithms that you've learned to be able to finally use that. That's the one that you want to choose to finally go ahead and do your stuff. So that's the purpose of the cross-validation set. It actually helps you decide which algorithm you want to use. So that will answer the second question, which algorithm that you want to use, right? So this decomposition assumes we know the algorithm to apply. Okay, so what if you don't? Okay, that's where the cross-validation set comes in. So the purpose of the cross-validation set, and I'll talk about how to make this later. I just want to get this clear. The cross-validation data set is to help decide which algorithm you want to choose, or which algorithm to choose for your problem. Okay? It's actually the best practice to, instead of just focusing on one algorithm, it's actually the best practice to try 3 or 4 or several different algorithms and see which one of these performs the best. And you choose whichever algorithm performs the best as your final model to use. Okay, so what we've seen so far in the lab is we just stuck with one algorithm. But you're probably asking yourself, well, I've learned all these different algorithms, which one is the best one? Well, 1, it depends on your data, and 2, just try all of them and see which one performs the best. Okay? All right, so it is usually, thank you, the best practice, to try a few algorithms and select the best performing one. So how do we do that? Well, I'm going to lay out that procedure soon. So I'll lay out these steps and then we'll go for a break. Okay, so here are the steps for choosing the right algorithm. Okay. Well, the first step is to actually choose any algorithm you want to try. So the first step is to just pick one algorithm that you want to try, whether it's logistic regression or neural networks or support vector machines. Just choose, decide on an algorithm that you want to try. So decide on an algorithm to try. If it's SVMs or neural networks or support, or logistic regression. There's so many different ones that we can try, etc. Okay, and I'm talking just classification here. So 2. So first figure out the one that you want to try, and then the second one is to decide on the initial. Decide on the initial structure. So for logistic regression or whatever, decide how many features you want, and then for neural networks, you want to decide how many layers you want, how many hidden neurons you want per layer. For support vector machines, you might want to decide on the kernel. So what you're doing here first is just deciding some initial structure or some initial architecture of your system so we can actually just see what the results look like. So just choose some initial structure first. Okay? So decide on initial architecture. Let me just lay out these steps and then I'll take a break. And then I'll continue after. Okay, I'm almost done. That's good. So decide on the initial architecture, right? So for example, select the number of features, right? Or select the internals. Sorry, select the internals. So what I mean by the internals is, for example, if you had neural networks, choose the number, the number of layers. Number of neurons per layer, and so on. Number of neurons per layer. Okay. If you were taking a look at support vector machines, the kernel function, something you want to try. You want to try varying. Right, and the parameters of the kernel. And so on. So just choose some initial architecture. Okay. And then what you're going to do is you're going to use the training data to find the best parameters. So in literature, when they say to find the best parameters, what they mean is that they are training a model. Training the model. So that's also the acceptable, the acceptable language too. Okay? So then what you're going to do next is you're going to use the cross-validation set. To tune the model. So the purpose of the cross-validation set is to be able to tune the internals parameters of the model. So for example, let's say you have your initial structure and you decide to run your, find the best parameters and you want to see what the, use this to figure out what the accuracy is. If the accuracy is not to your standard, then you would tune the parameters slightly, whether you increase the number of hidden layers, increase the number of neurons, run through the training set again, and see what the cross-validation is. So you're going back and forth between the training set and the cross-validation. So the training is used for training your model. The cross-validation is used to assess the accuracy of the model. And if the accuracy is not to what you expect, you got to go back and maybe change a little bit of the model, and then go back and forth until you're satisfied. So the cross-validation set is used to tune the model. Okay, so what you could do is you measure, I'm almost done. I've only got like 2 more steps and we'll take a break. Okay, so measure overall cost and classification accuracy. First, using train model. Okay, so that's the 4th step. Okay, so if the accuracy, so this is step number 5, if the accuracy is not acceptable, okay, change the architecture. Some examples would be, for neural networks, change the number of layers, number of neurons and so on, so you can change these. Okay. For support vector machines, you might want to change the kernel. Or, change whatever you can that is a variable in the training process to be able to get the accuracy up. Okay? Or you might want to change the number of features. You might want to add regularization, and so on and so forth. So, this is where you would actually tune the parameters. So, step 5, if the accuracy is not acceptable, this is where you would tune. And then what you do then is 6, using changed architecture, retrain model to get the right parameters. Okay, with the training set. Almost done. Okay, and then what you're going to do is you're going to repeat steps 3 to 6. So repeat steps 3 to 6 until the accuracy is acceptable. Whatever that is subject to you or subject to your employer until the accuracy is acceptable. Okay? And then finally, last but not least, what you're going to do is you're going to use the test set. So now there's 3 different portions. You have the training set, you have the cross-validation set, and then you finally have the test set. So the test set is used to assess the overall performance. So this is what you would actually be simulated if you were to put this in practice, where you actually didn't have access to these examples and you want to see how it's like when it predicts examples it hasn't seen before. Okay? So finally, use the test set to measure performance. Okay? So measure performance, and then let's see here. This mimics data not seen in training and tuning process. Okay? And then what you do is you do not tune the model with the set. Okay? Okay. And that's it. Okay, let's take a break, and then we'll come back and I'll finish up here.